Hey, welcome back, everybody. We have a really awesome integral for you today. This includes Pythagorean identities, double angle formulas, U substitution, and a surprise, improper integral. So much Calc 2 in one integral. And we actually get to be really clever about the way we use these. So let's recall some things that we're going to need before we dig in. So I'm going to say recall the following. So we're going to need that classic Pythagorean identity. So cosine squared of theta plus sine squared of theta, of course, is 1. We're going to need a double angle formula. So cosine of 2 theta, that's equal to cosine squared of theta minus sine squared of theta. And maybe I'll let the rest be a surprise. Okay, so I think without further ado, we should check this thing out because it's a fun one. All right, so we've got the integral from 0 to pi. We've got dx over 5 plus 4 cosine of x. And at first glance, it seems like what on earth can we do with this, right? And what could we possibly do to make this solvable? But here's where we get to be kind of clever. So let's note something that's it might seem kind of silly, but it turns out it's not silly. That 5 is equal to 5 times 1. So a little happy face there. Okay, and let's also notice something. So based on the double angle formula, right, we said just a moment ago that cosine of 2 theta was cosine squared of theta minus sine squared of theta for any theta. So we can actually be kind of clever about our choice of theta. We can actually choose x over 2 to be theta. So if I plug in x over 2 here, that'll just give me x. And if I plug in x over 2 here and here, that gives me the following. So I've got cosine squared of x over 2 minus the sine squared of x over 2. And the two places that we're going to be clever are here, using this, and then right here, using this. So the question is, how are we going to be clever with this 5 equals 5 times 1? Well, think of a useful way to say 1 in this case. A useful way to say 1 is, of course, with the Pythagorean identity. We just want to say it in a way that's compatible with this, right? So we must have the cosine squared of x over 2 plus sine squared of x over 2. That's equal to 1. That's the clever 1. That's the smiley face, cheeky little 1 here that I'm going to replace that with. Okay. Okay, so with all of these notes, we get the following. So let's see what we have here. We've got the integral from 0 to pi. Dx is just fine, and I want to give myself a lot of room. So 5, we said, is 5 times 1, and this is the 1 that we want to use. This is going to be our clever form of 1. So 5 times 1, but this is our 1. So cosine squared of x over 2 plus sine squared of x over 2. And then here, we're going to replace this with this. And notice the angles are all compatible now. Okay, so it looks like goodbye cosine of x. Hello, cosine squared of x over 2 minus sine squared of x over 2. and we'll see how that's helpful. So this is the part that's maybe a bit sneaky, right? Having to realize or reimagine one is this. But I think in mathematics, when you're exposed to tricks, you're able to add them to your arsenal for problem solving. So I think that's actually quite valuable. Imagine distributing and then combining like terms. If I distribute and combine like terms, I get the following. So 5 cosine squared of x over 2 plus 4 cosine squared of x over 2, that's going to give me, it looks like 9. So that's 9 cosine squared of x over 2. And let's see here. So 5 sine squared of x over 2 minus, right? So minus 4 sine squared of x over 2. That should be 1 sine squared of x over 2. Okay, so another opportunity to be clever. So let's note the following. So we know that tangent squared of theta plus 1 is equal to secant squared of theta, right? That's another really famous Pythagorean identity. Well, this will be useful if I could set up some sort of substitution. Like if I had some sort of tangent that I could call u, then du secant squared, if I could get that to show up, then I could make some sort of use out of this. Okay, so let's do the following. So let's multiply the top and the bottom. So here's where we get to be clever. By 1 over cosine squared of x over 2 over itself. Okay, so here I'm just going to distribute downstairs. And then upstairs, I just need to realize that 1 over cosine squared of x over 2, well, that's exactly secant squared of x over 2. Just by definition of secant. So it looks like I've got a secant squared, which seems maybe promising. We'll find out in a moment. Of x over 2. We've got a dx. Okay, so here's my secant. And then let's see down here. So we've got 9. And then sine squared over cosine squared, that should be a tangent squared of x over 2. Again, this is really promising, right? Because tangent and secant squared are, well, they're related via derivatives. So it looks like I should make a substitution, but we want to be really careful when we go to change our bounds. So how about u is equal to tangent of x over 2? And then the derivative, so be careful to use the chain rule, right? So we've got secant squared of x over 2, and then times the derivative of the inside, which is a half, and then dx, of course. Now here's where we need to be careful. Since I'm switching variables, I need to switch bounds. These bounds are only relevant to x. I want bounds that are relevant to u. And we're going to get a bit of a surprise. So new bounds. Okay, so my lower bound, that's x equals 0. So x goes in for x. Remember, we go to the substitution statement. So u is equal to exactly tangent of 0 over 2. But that's exactly the tangent of 0, which is 0. For the upper bound, I'm actually going to be really, really careful here. Because if x is pi, I have to be careful, right? So because I'll be looking at pi over 2. And so let's note something. So tangent of theta goes to positive infinity as theta goes to pi over 2 from the left. So what that means for me is that this upper bound is infinity, right? This is actually an improper integral. It's unbounded. And I know this is true, right? So thinking about tangent near pi over 2, just think about the graph of tangent with that little vertical asymptote here at pi over 2. And at negative pi over 2. And you can see as I approach pi over 2 from the left, tangent goes to infinity. So that's why the upper bound is infinity. Okay, so what do we have from our substitution? So this is actually, so I want to replace this. So maybe I should multiply both sides by 2. Okay, so I can replace that with 2. Looks like du. And then downstairs I've got 9 plus u squared. Well, that's really good because that looks like a classic arctangent form to me. So this is an improper integral, so we want to treat it carefully with limits. Maybe I'll note this. So this is an improper integral. Okay, so let's see where that leads us. Okay, so with improper integrals, let's introduce a limit. Let's call that upper bound b, and b will go to infinity. In calculus, we sort of tame the infinite via limits. Okay, so what do we have here? We've got 2 times the limit. So if I take the antiderivative, I've got 1 over a arctan of u over a. But we need to evaluate from 0 to b and then limit last. Or at least limit after this. Okay, so I think the hardest part of the problem is over. So let's see where this takes us. So it looks like I've got 1/3 times the arctangent of, looks like b over 3 minus, by the fundamental theorem of calculus, minus 1/3 arctangent of, well, 0 over 3 is just 0. And for this limit, you can just think about the graph of arctan. That's concave up, inflection concave down. Okay, so that's just y equals arctan of x. So let's see what happens, right? So as the input gets arbitrarily large, that means if we run forever to the right, well, as this input gets arbitrarily large, the graph of arctan gets closer and closer and closer to pi over 2. Okay, so we got 1/3, we got pi over 2. And this will be 0. We know that the limit of a constant would be exactly that constant, in this case, 0. So it looks like our improper integral yields pi over 3. Quite a cool integral. It reviews a lot of Calc 2 and throws in a little bit of cleverness with trig. I like it.